Just now, we can get the information that the application is crashed, and Microsoft or operating system, they close the application, they force the close the application. But the question is, I want to know what is causing the application crash, because I just sent so long a characters. Okay, a lot of debuggers. You can use a lot of debuggers like IDA debuggers or Immunity Canvas or WinDebug or this one of my favorite because it's simple. I'm gonna use Oli Debug. It's a free debugger in here, so I can use Oli Debug. So I have Oli Debug. Okay, this one is just a small application and it's easy to understand, and even the feature is not much, but it's enough for you to learn the basic of the basic buffer overflow. All right, I already run the Oli debug. Okay, and because we are going to see what will be happening, what inside the application when it crashes, so we can run or attach the exe file. We can attach the exe file. Okay, I'm gonna attach this mini-share.exe into the debugger. All right, before we go to the next step, I will explain to you what is what the interface of the debugger. Okay, when you load your application into debugger at the first time, it won't be run. If you look at this, it won't be execute. It will be paused at the first time. And in here you can see, okay, this is the sections in the debugger. Most of debugger, they have 4 sections like this. So this is the first sections of the debugger, which is this all the instruction in the assembler language. Until you press play button, then your application will be run. And this is the memory address of the first instruction. Remember, if you click and play, it will execute this push add, move ESI, and any other, and so on and so on and so on, depend on the instruction. And on the right side in here, this is the most important one. This is the to show you the value on in the CPU. We have EAX, we have CX, we have DX, BX. Oh, but what is this? Why we have EAX? Why we have ECX? Why we have EDX? Because we are in the 32-bit operating system. In the 16-bit operating system, we have AX. If you are in the 32-bit, we have extended EX. If you are in the 64-bit, we have REX. Okay, so that's just a simple difference. Okay, because we are in the 32-bit, you'll see the length of EX is 1, 2, 3, 4, 5, 6, 7, 8 hexabyte. Okay, and then you can see this CX, DX, this is the main registers until this one. Remember, this is the base register. And another important register is this one, ESP, which is this the index register. ESP value is always ESP is always pointed to the value on the stack. So where is the stack? You can look at this. Okay, in this window, this is actually our stack. Okay, our memory, our stack memory. Okay, all right. Depends on the debugger. Okay, if you know the concept, the stack is actually start from the on the top. This is the top of the stack, and this one is the bottom. It's supposed to be like that, but to make it easier, actually this one is the bottom of the stack, and this one is the okay. So the stack is growth from the top to the bottom. Okay, but actually in the real world, in the real world, the stack is going from the bottom to the up. Okay, all right, and then look at this. And this the yep. Oops, sorry. This one. Yeah. Okay. FPU is the floating processing unit. Yeah, this is in the normal modern CPU. They don't call this. Last time we use CPU, and then we have another extended CPU like in the Intel 80386. They have CPU, and then they have another MMX. It's called MMX. EPU is for same like CPU, but they have another extension to do arithmetical calculation. Okay. Now, this is the location on the stack, and if you run the application, the stack is pointed to here. And look at this. This is another important value, right? EIP. Okay, what is the EIP? EIP is actually the to tell the CPU to go to if you execute this application, CPU will go to the address and execute this address instruction pointer. Okay, so if you look at this, EIP is pointed to 00960000, which is this is the mini share module entry point. Okay, all right. What is in here? In here is some part of location that you can look at the real memory value in the hex dump. You can look in here this because by default this is the memory location, and then this is the value in the memory in this address 00961000, and this one is the instruction. For example, if I want to follow the stack in the dump, you can click in here, follow in dump, so you can see this is the memory location in the stack. Hex dump, okay, 0023 FFC4 4F blah blah blah. This hex dump. Look at this. This is the hex dump. 4F, 6D, 41. Okay, so this space is actually if let's say you want to debug in the next level, in the advanced level of overflow or research, you will use this very frequently. For example, I want to find out where is my cell code, where is my payload. You can right click in here, for example, and then follow in dump, like that. Okay, so this is stack pointer, follow in dump, and then this AIP, and yeah, appearance. Okay, in here I'm gonna follow in dump. Okay, all the selection. So this is actually all the instruction. Okay, don't worry about it. I will try to make it very slow, not very slow, slowly but easy and simple to understand. Okay, so at first it will be false, and then after that we're gonna run this application. Okay, I have this mini share running and attach this IP address, and then yes, because we want to see in here how we can run how the traffic coming in and going out, then you can restart the traffic capturing, and then after that we can resend again our eval buffer. So we are ready in here. We already set everything. Our Wireshark ready to capture the traffic, and we already run the mini share, but inside the debugger. And then we're gonna resend again our minisploit1.py, which is sending get a 22220 characters. Enter. All right, and then try to look in here. Okay, wonderful. I don't see anything in here yet. I will scroll down. Yep. Yep. All right. Look at this TCP segment get AAA. Same like before, but now we are running inside the debugger and just wait for a moment. Yep. Wonderful. I got the blinking in here. Why it's blinking? Because we are run this application, execute this application inside the debugger, and the debugger will automatically pause or stop this application because there's a problem with this application. Okay guys, if you look at this, why this application crash? Okay, thanks to the debugger. Look at this. Application is paused. Our debugger automatically close the application or stop the application. And why? The question is why the application crash or pause? Look at this error message first. Okay, access violation when executing 41. Okay, this is very interesting. Interesting. Okay, our apps try to execute okay the instruction in 41. Okay, so this is another this is when you see something like this, we have one good news. So this is the first good news. Okay, first good news is our apps try to execute instruction in 41. No wonder our debugger they close this application because our debugger they will tell to application, hey application, why you are going to execute this 41, which is 41 is beyond your allocation memory. Yeah, all right. So that's the first good news. The second good news is if you look at this in the stack, this is a second good news. Okay, the second good news is all right. Okay, good news. Okay, we managed to fill in the stack. We managed to all the stack value. All the stack is filled in A or 41, 41, 41. Okay, why I said this is the second good news is because 41, 41 is familiar was. Okay, 41, 41 is a part of our evil buffer. Remember just now we are going to send 41, 41, 41 or A character for 2220. Okay, so if we can draw the diagram, I will go back to diagram again, right? Just now, okay, let me put in here, all right, or in here maybe, okay, or in here, yes, okay, no problem. Yeah, we have the stack in here, all right, and then after that in here, just now we are sending long buffer, okay, yeah, just now we are sending the long A and then A, Okay, I don't need to put all the 2220. It will just put something like this. Okay, but I still need to write in here because later I will show you where we can put or where which part of A will replace into the EIP and which parts of A will replace into the stack. All right, so just now, okay, the basic concept, okay, I can delete in here. So we have another what you call this good information in here. When we send a long string, okay, I can delete this part. All right, I can move in here. Okay, the stack maybe I will put in here. Right it up, and yep, this one. All right, I can move in here. Okay, this is good. Okay. Okay, so we have two good news. The first one is we managed to replace our instruction pointer. Okay, but we don't know where. Okay, so some part of our buffer, we don't know. Maybe in here, maybe, because we don't know yet. All right, we don't know. Maybe in this location it will replace to EIP. Okay, EIP replace in here. Okay, replace. All right, so that's why when you send we get in here another, yep, EIP is 41, 41, 41, 41. Why? Okay, let's take a look at this again. Access violation when executing 41, 41, 41. Why you get this error message? Remember who control the flow of the application is EIP. And we managed to replace or smash or we managed to replace the value of EIP with 41, 41, 41. So we have two good news. EIP is replaced to 41, 41. No wonder our application will try to go to 41, 41. Which is this 41, 41 is not in our it is somewhere in the in the memory. And also another good news is ESP. Okay, right? ESP is pointed to somewhere. Okay, so when we put in here maybe 1, 2, 3, 4, 5. Okay, I'm gonna put in here 1, 2, 3, 4. Okay, this one. EIP replace. Oh, sorry. Yep, like this. Okay, up. Maybe in this location. And 1, 2, 3, 4. But okay, okay, maybe in this location, but we are not sure yet. Okay, I'm just try to draw ESP. Okay, so some of our value it will go to the stack. Okay, as you can see in here, look in the stack is now 41, 41, 41. So if I can draw a diagram in here, the stack value is 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, 41, and so on and so on and so on. Okay, and the good news is in here you can see, remember what is the value on the stack? if you look at this is the location on the stack. I will copy to the clipboard, and then you can see in here, this is the address, the first address on the stack. 0C, yeah, like this. All right. Okay. I'm gonna put this the first line on the stack. So the other good news is ESP is pointed to this address 0C AC3908. And in this first address of the stack, okay, you can see in here, yep, yeah, we can manage our stack, and then it will fill in by 41, 41, 41. So if I can draw again the diagram, the stack pointer in here will replace to 0C 01 AC3908, which is this is river, or this one is right, this one is go to this one, right, this one pointed to this address, which is we can insert the stack. So what is the meaning of this? Why this is a good news? First, if you know exactly how many bytes before overflow, or basically this is called the safe buffer, safe buffer. All right. Okay, I'm gonna use the small font, save buffer. All right. Okay, so normally we can put this the A part. Okay, A part, yeah, where we can put the save buffer, and this one is the B part. Okay, where later on we can put something into to replace EIP, and this is C part. Okay, where later on we're gonna put the payload. Okay, so that's why just now we can our application has been stopped by the CPU, by the debugger, is because our CPU try to go to this memory location address. Okay, CPU will say, okay, I will go to CPU will say, oh, okay, oh, okay, I will go to 41 to the address of 41, 41, 41, 41, and execute the code in there. Okay, but because 41, 41 is beyond our application, so it will be rejected, or it will be crossed by the debugger. Okay, now we know the application interface. So now I will try to we're gonna do the next step. All right. Okay. So we know that our application in here, they cannot handle the data more than 2220. So now how many bytes, which is actually exactly before the buffer is overflow, or what is the value, or what is the location of this position? Okay, because in here later on we're gonna put something to redirect the application to execute our payload in here. Okay, there are a few of methods to do to find the correct position of the offset. The old method last time, okay, why I said the old method is, for example, you can do in here. First is you can do splitting. Okay, what is splitting? Splitting is basically you send at first, like just now, a character for 220,000 bytes. Okay, so this is called splitting. Yeah, so that's why the reason why I put 2,220 characters. So in here we're gonna put a splitting 22220. Okay, all right. Okay, splitting is basically you send at first this A, all right, and then on the next step in here, you split into a half. Split, okay, split by basically, okay. Now after you send A for 22220 character, you can split into 1110, and the other part of your buffer is 1110. Okay, so here you can put in here B B B B B A, okay, A, or B B B B B. Okay, so if later on you will see that EIP is replaced by BBBBB, or if later you see the EIP is replaced by 40, 40, 40, 40, which is the character of BBBBB in hexadecimal, 40, 40, 40, 40. In here, that means you can concentrate on this area. That means the buffer is more than 110. Then you can split again on the third type. You can re-split again. So you can send another A, in here 11110, okay, and in here you can put another B, all right. So in here you're gonna split into two parts again, okay. So I'm gonna split in here 5, 5, 5, 5, okay, and another 5, 5, 5, 5, okay, in here, yeah, 5, 5, 5. So this one is gonna be B, and this one is gonna be C. Okay, so I'm sure you can get the logic in here. If later on the EIP is still replaced by 42, 42, then you can concentrate in here on this location only, because the buffer may be around 110 plus 555, but no more than 555. So that is called splitting techniques. All right. Logically or theoretically, after maximum 6 split, okay, you will get the correct location of this EIP or replace. Imagine in front of your desk you have a paper, just as a paper, a printer paper, yeah, and then try to split in half, and then after that split again in half, and then after that split again in half, and then split again in half. Okay, so after 6 time, yeah, I'm sure when you try to split again in a half, fold, yeah, you fold in a half, fold a half, fold a half, fold again, until 6 time it was almost impossible for you to fold the your paper. You can try it right now in your in your home. Okay, okay. So this is the more accurate method. Yeah, last time you can use splitting, but it will take time. But again, thanks to the tools. Yeah, what I mean by the tools is now there's a lot of tools. Yeah, same like just now or a few days ago or this few days we already learned how to exploit the machine. We can use. You don't need to think about compiling. You can just metasploit. But how it works? This in our class. We are going to learn about this. Okay, so maybe some of you guys have an idea. Oh, Billy, what if we send unique characters? What do you mean by unique? Okay. If you know this is the safe buffer, why don't we just send a unique characters? Unique characters, like for example, don't send just A characters. Send A to Z and lowercase A to Z and so on and so on and so on. Good idea, right? And makes sense. Okay. Yes, alright. So if let's say I'm gonna send in here a unique characters, A, B, C, D, E, F, G, G, and then after that F, J, K, L. Okay, something like that, or something that is unique, something that is not the what you call this, not the normal character. I, J, K, L. Make sense? Okay. Yeah, why don't we why didn't we do this? Okay. All right. Okay, this is another good example. Yeah, why don't we just send a simple, or just send what just send unique characters, unique string like this. Okay, I give you another example. This is maybe a good idea if the string that is the byte that is allocated for this buffer is only less than 26 or 127. Because why? If let's say you have a character set A to Z and A to Z again, A to Z again, okay? A to Z is how many characters? How many bytes? 26 bytes. And then, okay, Billy, we can get another A to Z again. So I'm going to send A to Z, A to Z, and then plus with A to Z again. Okay, A to Z again. So this one is 52 bytes, right? 2 bytes. Okay, okay. It's a good idea. You can try. You send A to Z, A to Z. But what if in the EIP later on replaced by IJKL? Okay, if EIP is equals to EIP is replaced by I, J, F, A, B, C, D, F, G, H. Oh, sorry, I forgot. H, I, J, K, L. I missed one character. It's okay, no problem. Yeah, so this one is the H, I, J, K, L. Okay. A, B, C, D, F, G, H, I, J, K. Yeah, something like that. Okay. And then H, I, J, something like that. Okay. If you send this kind of unique characters, maybe it works, but maybe what if the character is more than 52 bytes? You will get confused because is this HIJ coming from the first set or is come from the second set? So you will still get confused. Okay, because you don't know maybe this is from the first one or this one. So that's why just now I show you the splitting techniques. Okay, Billy, maybe what if we send long characters like a combination of A to Z, and then after that we send another characters like, for example, lowercase A to Z, and then after that A to Z again, and then A to Z again. Okay, is that enough? 26 plus 26, 56, 56 plus 56, that means 112 bytes. Okay, okay, so it looks good, but what if EIP is replaced by what? Okay, let me just A, B, C, D, something like that. Again, you will be confused. Is this A, B, C, D come from the first set or this one is from the second set? Okay. All right, so splitting is the old techniques. Yeah, like just now, you can do splitting, yeah, send A, and split again, split again, split again, split. But it was like a lot of time. Okay, thanks. Nowadays we have a lot of tools. We can create a unique pattern. Yeah, considered under quote theoretically unlimited unit pattern. Okay, to create a pattern that is unique and after that you can easily identify when EIP is replaced by something, then you can easily identify the position of EIP. Okay, so from here, you can see I'm going to use another tools thanks to Metasploit as well. Okay, Metasploit have another tools called pattern create. Okay, so that's why I said since there's a Metasploit, hacking is like in the movie. So you can go to pentest in here, pentest, all right, and then exploit, and then framework, and then cd tools. There's AL. Okay, look at this. There's a lot of tools. Okay, this is the tool that we need pattern create and pattern offset. So I'm gonna clear this one. Okay, let me show you how to create pattern offset. Slash, for example, in here, pattern offset dot rb. How many pattern do you want? 20 bytes. Okay, look, very fast. Oops, pattern offset. Oh, sorry, pattern create. Let me clear this one first. Pattern create. Pattern create .rb 20 bytes. Enter. Then you will see in here. Look, AA0, AA1, AA2, AA3, AA4, AA5, AA something something something. If you look at this AA0, AA1, is this a unique pattern? No. Yeah. If you look at this, really, is this really unique? Yes, because they use hexadecimal, and secondly is they count by 3 bytes. So AA0 is the first set, AA1, AA2, AA3, and so on. So if let's say your EIP later on replaced by AA2, something like that, you can just use these tools, pattern offset, okay, pattern offset.rb. Hi Metasploit, please tell me where is 1AA, for example, like that. And then you can look at this. Yep. Be careful when you calculate the pattern AA0. 0, 1, 2, 3, 4, 5. Okay, it start from 0. Be careful, this is the byte number 0. This is number 0. So 1AA. So that's why they said this is start in the position number 5, because this one is from 0. Okay, all right. Look at this. We count it again. 0, 1, 2, 3, 4, 5. So 1AA is in the fifth bytes in our pattern offset. Okay, you got the idea? All right. So now we can ask these tools again. Hi, Metasploit, can you please give me a pattern create? Okay, can you create for me a pattern for 2220 bytes? Enter. Wonderful. So you can see from here, look, this is all the pattern, and then this one is 2200 byte. Very good one. Okay, so if later on after you send this evil buffer to the application, and then you can see, okay, for example, EIP is replaced by which one do you want? Maybe this one, CN6. Okay, so if EIP is replaced by CN6, you can just use these tools again. Okay, and then you can ask, hey Metasploit, where is the position of pattern offset? Okay, .rb. This is CN9, or it's up to you which one you want, CN7, CN6. Okay, I'm going to use this one, CN9. Okay, you can just ask this tool, CN9 is in which offset or position. Enter, and then look at this, wonderful. This is in position number 19777. 1977. You believe it? Yeah, if you don't trust it, you can count 0, 1, 2, 3, 4, 5, 6, 7. Of course, of course, we don't need to count the bytes. We just trust these tools. Okay, so this is a very useful tools. You can create the pattern offset. So now I will go back again to our exploit skeleton. Just copy all of this pattern unique pattern, and then we're gonna have the second second skeleton exploit code minisploit2.py. All right. Oops, sorry. Nano nano minisploit2.py. All right. Okay. If you look at this just now, okay. The hero is still the same. User bin Python, import socket, target address, target port, and then buffer get. And look at this buffer. Just copy all the pattern just now. It is a long line, 2220 characters, and don't forget to close the end of the buffer with the HTTP close conversation. Open the socket, connect the socket, send the buffer, and close. Okay, so now I will go back again to our target machine. In here, we're gonna restart again, because this machine has been crashed. Then you can restart using click on debug and then restart. Ta-da! Yep. Okay, let's go. Yep. And then I'm gonna play this application. Correct. Look at this. Yes. Okay, we get the mini-share exe application, and then if you want as well, you can run Wireshark, because we are going to send a unique pattern to the remote machine. Capture, restart. All right, that's cool. Okay, then we can try to send our second exploit, or second skeleton of our exploit, which is here we are going to find the offset. Okay, Python minisploit2.py. Enter. Yep. Let's take a look in here. And then you scroll down. I want to see the pattern. Okay, NBNS. All right, good. Look at this. Get AA0, AA1, AA2, and so on, so on, so on. It is our unique pattern. And just wait until the application close. Yep, the application is closed. And yes, if you want to check in here, you can see we are sending hypertext protocol, and then get. Okay, look at the data itself. Look in here. This is the data. Get AA. Okay, we can If you want to make sure, you can right, look at this, get AA0, AA1, AA2, AA2, wow, so many, 2220, okay, and then HTTP 1.1 and so on. Okay, that's good. That means we managed to send. And if you look at this, our application is crashed, and it will be good, because just now we can get another information. Look at this, access violation when executing 366.84335. Okay, why our application try to go to this address is because, remember just now, we can replace our instance pointer with the 366.84335. And if you look at this, our stack is also filled in by a part of our pattern, CH7, CH8, CH9, and so on, which is this in the hexadecimal, on this location, on this memory location. All right, so now we can draw back again, we can go back to our diagram. After we send a unique pattern like that, right, we can send in here our unique pattern, in here, blah 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 blah, okay. EIP is luckily EIP, we can get a value of EIP. EIP is replaced by one of a part of our pattern. I will copy this to the clipboard, and then I'm gonna put in here, EIP is now replaced by our wonderful pattern, 36684335. Okay, and that means EIP in here, is not 41 41 41 again. EIP is now replaced by this value that we are going to find out what is the place of that. And another good thing is, in the stack, we can see in here the stack. I will copy to the clipboard, copy selection to the clipboard, and I'm gonna erase this one, delete this one. Okay, all right, delete, and then we can fill in here, EIP. Sorry, EIP is now the value of EIP. I will follow to in the DOM. In here, look at this. This is our EIP. Copy to the clipboard. Okay, actually there's a lot of string in there. All right, look at this. All right, this one. Okay, and yeah, 41, so on, so on, so on. CH7, CH7, so on, so on. Okay, no need to copy all those things. I will just put all some of the lines, because there's so many. Oops, sorry. I will copy just one of the line in here. Okay, look at this. I will delete this one. Where is the CH7? Okay. Ta-da-da. Wow, so many. Okay. Yep. CS7, CS8, up. Sorry. CS7, CS, and so on. Okay. And another good things in here is, if you look at the stack pointer is pointed to this address, copy to the clipboard. So the stack is replaced to this address. And look, okay, I will show you later on why this is quite dangerous, because you must pay attention to this one, because the stack now is pointed to 103908. Okay, look at this. This is different with the first one, 01 AC3908. Okay, because why? Stack is dynamic. Stack is used by another application. So in some case later on, you will see that the stack position is not in this address anymore. Okay, because this stack is really dynamic. If you have another application is running, if you have another application is or a lot of application is open, maybe the stack value will not be in this address anymore. And this is quite important, because we are going to learn about the trick how we can redirect our stack or our CPU to execute the value on the stack. We know in here EIP is already replaced by this value. EIP is replaced by this 3668. Okay, like that. Okay, so from here we know exactly, we can get the information that EIP is replaced to this string. Okay, so if I can draw in here, I can write in here, this is the B part, or basically the buffer when replace EIP. So EIP is replaced by 36, and then 68, and then 43, and then this is 35. Okay, so this is a good news, guys. Okay, but the question is, what is the location of this? Okay, we need to find. Okay, this is the safe buffer, and this is the buffer when we can replace EIP. Remember just now we can use the tools that pattern offset to find out how many bytes before its overflow, or where is the exact location of this, and also where is the location of these stacks. Okay, because the stack is pointed to CS7, CS11, and so on, so on, so on, so on. Okay, so we can go back to our backtrack or metasploit, and then we can ask in here, you can use a pattern offset. Okay, pattern offset.rb, and then hi metasploit, I want to know where is the, okay, this 36684335. Okay, pattern offset.rb 3668, what just now, 36684335. Okay, 4335, enter. And then look at this, wonderful. We managed to get the position of this. So the buffer in here, before it replaced the IP, the location in here is, what is the location in here? 1787. Wonderful. Okay, so this is the location of EIP. And the other thing is, I want to know the location of this, the stack. Okay, because the value in here is replaced by CS7, CS8, and something like that. So I can ask pattern offset again and ask CS7, CS8, and something. Oh, sorry. Yep, it's okay. They found that this is the location, 17. Okay, so I can draw in here the diagram. All right, when we can manage, we can replace the value on the stack 1791. Okay, wonderful. So this is the location where we put the C87 or something like just now. In the ASCII or in the hexadecimal. This is the 40. Okay, copy to the clipboard, and I'm gonna put in here. So this one is the value. When we replace the value on the stack 43, 37, 68, 43, and so on, and so on, and so on, and so on. Okay, good news. All right. Okay, so okay, let's go to the next step. Right. Since now you know already the safe buffer is how many bytes before its overflow. How many bytes? The safe buffer in a part is 17800, 178 1787 bytes. Be careful, because it start from 0 to 1786. Okay, before its overflow. Be careful, it start from 0. Okay, now let's take a look at the logic. If I can replace EIP with this value, EIP replace with this value. All right. Okay, EIP replace with this value 36683445. Okay, logically like this. If I am the CPU in here, when the buffer is overflow, and this value, EIP, eh, this value when you put in here into the EIP, and then you go to the EIP replace to this value. Okay, and then if you look at this, EIP, is actually replaced to something. Okay, so you can get the idea. What is the purpose of EIP? All right, instruction pointer is to tell the CPU, CPU, okay, I will go to okay, this address, and execute the instruction there. Okay, I will go to, okay, I'm going to put something in here. Okay, something. All right, so what you're going to put in here? The address of our payload. Okay, so you need to trick the user, the CPU, CPU. You need to trick the CPU. Hi CPU, why don't you go to the address of the payload, of the payload in the stack. Okay? Yeah? Okay, I will go to something and actually okay. So since you are able to replace the EIP, look at this. This is a magic. Eh? Look at the address of the stack. The current address of the stack is this one. 10373904. Make sense? And this one is the content of our payload. If you look at this, look, EIP is in here, okay, and ESP is in here. All right. So if you want to, if you want the CPU to go to the stack, why don't you just put the address of the stack 01373908? Put into EIP. Make sense? Okay. So in here, instead of I'm gonna put 363684335, why don't I can just put the address of the stack? The address of the stack that I know so far, the current address of the stack is this value. Copy to the clipboard. So this is the address of the stack. Yeah? Look at this. Alright. So this is the address of stack 0339. Okay, what if I put this in here? Okay, I'm gonna put in the blue color in here. Okay, in this location. Alright, I'm gonna use blue color. Okay, oops, sorry. Okay, like that. Okay, in this location exactly when it's overflow, why is not changed to blue? Oh, okay, blue. All right, so I'm gonna put this address 3908. Okay, what will be happen? EIP will be replaced by this stack address. Okay, correct. And then after that, again in here, EIP will be replaced by the stack address. Look at this. Okay. Okay. So when the IP is changed to that address, what will be happen? Look at this. Good. Wonderful. Yeah. So what is the meaning of this? EIP replaced by 013739, which is this is the value of the current stack. Eh? Which is this is the address of the stack. The address of the stack. Wonderful. Okay? So if you manage to replace EIP with the current address of the stack, IP will become to here, and then in here CPU will look at this address. Okay, all right, look at this. Okay, I will go to this address. Okay, then CPU will get tricked. CPU will go to this address, and then voila, this address is actually your payload. Wonderful. Look at the idea. Eh? So when you okay, let's say you can just put A in here as normal. A A A. But in the byte number 1787, you put 013739, which is this is the current address of the stack. See? And then the IP will replace with 0127. CPU will look at this. Oh, okay, I will go to this. Yeah. Okay, and execute the instruction there. Then CPU will jump. Yeah, CPU will go. Yeah, will go to the address pointed by stack pointer. Oh, pointed by EIP. Okay, which is in our what in our stack, we already put our payload. Sounds good? Yes. Okay, but unfortunately, guys, theoretically it works. But unfortunately, this one doesn't work. What is the reason? What is the reason this one doesn't work? Okay, theoretically, if you look at this, oh yeah, okay, maybe I can put that one, and then after that, I can put the AIP, and then I can redirect the control of the application to execute my payload that already put in the stack. Okay, and like I told just now, theoretically it works, but unfortunately, practically it won't work. Why? Eh? Why? Because stack is dynamic. Okay, the value in here, if you look at this, we just lucky just now because we managed to smash or replace the value on the stack with this content. Okay, but remember this stack is used by all of your application. If you run, for example, in here in the target machine, if you run in here, if you have another calculator or accessories, calculator, notepad, or whatever, maybe when you rerun again, the stack location is not the same location. Okay, or basically technical in the technical terms, in here it doesn't work. It won't work. Okay, this one doesn't work, right? Why? First, stack address is dynamic. Okay. Secondly is okay. Secondly is dynamic, and then secondly is you cannot put. So that's why static or hard coded address, stack address in your exploit. Okay, so the third one is we must find a way, okay, or trick, to ask the CPU to just execute our payload in the stack regardless of the current stack position. Okay, so this is the answer of this problem, because stack is dynamic. Okay, you cannot put static IP address. Okay, sorry, inside pointer address. Okay, stack is dynamic, is always changing. Okay, if your computer is restart, it will be changing. If your computer is patched, it's always changing. And if there's another application, it's always changing. So we have the problem. Next, we have a problem in here, another problem. Okay, problem in here. All right. Okay, you cannot put a static or hard-coded stack in the instance pointer. Okay, stack address is dynamic, and static hard-coded stack address in your exploit, and you need to find a way, or a trick. A lot of tricks later. I will show you the simple one, the easy one, but you need to find a way or the trick where you can ask the CPU, or you can ask the CPU, regardless of the stack, or regardless of the what you call this, the position on the stack at that time, but just go to the stack and execute the code in there. Now we have another problem. First, theoretically, if you look at the diagram, you can see that if you manage to replace the AIP with the address, the memory address of the stack, then logically, theoretically, CPU will go to this address and then execute the our payload in the stack. Yeah? But I tell you, this one theoretically it works, but practically maybe it won't work because stack is dynamic and stack is used by another application, not only your application. So whenever, if let's say you change or you run another application or you restart the machine or you have a few applications running, the stack address will not be pointed into the same address like it here in this example. Okay, so we need to find a way. Yeah? We need to find a way or the trick. Okay, we need to find a way or the trick regardless of the position on the stack, regardless of the pointer on the stack to the point to the memory location. I just want the CPU, okay, or the processor to go to the memory location on the stack and execute the what? The payload over there. Yeah, so the answer is hi CPU. Okay, so simple like that. Hi CPU. Yeah. I don't care the location, the current, okay, position on the stack, but please, but please just go to the stack and run my payload there. Okay, so this is the idea. All right, actually there's a lot of tricks, a lot of techniques. Yeah, there's a lot of tricks, a lot of technique, but this is the most easy way, and this one is quite tricky because I can say easy to understand but a little bit tricky. Yeah, but this is makes sense. I mean, I want to tell the CPU, hi CPU, I don't care. Where is the location of the stack? Where's the position? But whenever you jump, just go to the stack because I already set up the payload on the stack. Okay, so how to do that? All right, so now I'm gonna delete this one. Okay, okay. CPU will go to the address pointed by AIP. Actually, a lot of tricks. For example, you can calculate how many bytes in the safe buffer, and then how many bytes where you replace EIP, and then where is the location of your payload, and then you can put in here, yeah, approximately, for example, 10 bytes or 20 bytes, yeah, after the end of the EIP, so it will be pointed to the address in here. Okay. Okay, but that one is a lot of trial and error. I mean, there is some obstacle as well, and because EIP must be address of something. Okay, if you wrongly calculated the stack, wrongly calculate the length of address in here, maybe your CPU will execute the stack, but it's not exactly on the beginning of your payload. Okay. Okay, so I give you one another trick, which is really interesting in here, and then you will see from here. Oh, maybe all this why, and so on, so on, and later on, you will see in the exploit DB, for example, why they use this and why they use that and why they borrow something, and this is the most commonly trick that you can do, and the most common trick and easy ways. Okay, in the assembler code, all right. In the assembler code, there is instruction. I will just give you the instruction. Okay. In the assembler code, there is one instruction. Just now we learned about move and then pop, push, and any others. Okay. All right. I will just give you the answer. To answer this question is actually very simple. Okay. In the assembler, we have this instruction. The instruction name is called jump ESP. Oh, what is that? Now, all right, jump ESP is basically we're gonna tell to the CPU, yeah, to jump to the memory location that is pointed by IP, by the stack pointer, and then execute the code in there. Okay, so to answer this question, we can use jump ESP command, because jump ESP is actually to jump to the stack, regardless of the position of the address of the stack, and then execute the code in there. So this is one of the trick. Okay, and most of the vulnerability researcher, they use this trick, or basically sometimes they call this as to modify the return address. Okay, don't worry, later on you can try to find out what is return address, what is the meaning of that, and so on. Okay, but in this example I will try to make it as simple as possible. So basically you want to modify the return address. Okay, return address is actually the variable or the address of the memory, where after you call a one function or one application, so the application must return back to the original function. Let's say in your application you have three functions. The first one is the main function, the second one is the login function, and so on, so on. So whenever they put the data on the stack, um, your CPU, they must store the value of the return address, so they will go back to the previous address to continue the flow of the application. Okay, so now the question is how to put this jump ESP in our buffer. Now we have another problem, and in here, how to put this command, how to put this command, how to put this command into EIP register. Okay, so why I said this is a problem, because this is instruction jump ESP. Okay, you can revert in here. You can search JMP ESP like that. Okay, and then you will see a lot of reference. Why jump ESP instead of directly jumping into stack? Need to be located in the DLL, buffer overflow guideline, simple stack based overflow, long, and so on and so on and so on. Okay, you can read from later on, but I will show you first. Okay, how to put this comment? All right, why I put this one? Because in here, let's say, oh, okay, Billy, I want. In that case, that means I can send the save buffer AAA for 1787 bytes, and here exactly in this location I can put JM space P space E space E S E S P space. That's it. All right. Is it gonna work? No. Yeah. Why? Because in the EIP, the value must be a memory address. Okay, so you cannot just put something like this in the memory address. For example, if you put JMPSP, ESP EIP will be like this, but this is yeah, this is just in our knowledge GMP ESP. Just this is just our assumption GMP ESP, and then after that it will replace the EIP register. Okay, with that, right? JMP ESP. Okay, okay. So if you put something like this, our EIP later on we will replace with this string. Our EIP will replace with uh, JMP ESP. And but this one I can say this is doesn't work, right? Because this one is must be an address. You cannot just put a string like this JMP ESP. This must be an address of the memory, where in on that memory location we have JMP ESP. So how to solve this problem? Okay, now I will explain to you a little bit about the again operating system, how it works, and then how they execute your application. Actually, guys, when you execute the binary file in Windows, or later on in Linux, you are not only executing the exe file. Okay, for example, in here you can see minishare.exe. Okay, Windows is a UI, graphical user interface, and that's why when you create an application in Windows, there will be any library like for the GUI library, Windows library, and any other library, CL32, NTDLL, kernel library, and so on. Alright, so the trick is try to, okay, so the trick is the trick Okay, first, try to locate, eh? Try to search JMP ESP instruction in the memory, in the memory, okay, and it must be in this exact location in the memory. Okay, so the question is how to borrow that one. The trick is like this. Okay, the second question, second is okay, under quote, borrow the address, the address. Okay, and the third one is put into uh, our cell code, our sorry exploit. Okay. Okay, the question is how to find the search Japanese memory, which is there's a lot of condition, and this must be static. I mean, the jump ESP instruction must be always at the same memory location, even if you restart the machine. Okay. Alright, like I told you just now, when you run Windows application, you are not only executing the exe file, you are also executing or loading another DLL. Okay, I will show you in here. Just click on View and then Executable Modules, and then you will see this is all the library. Wonderful, all the library that is needed by this exe file, DLL, 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 DLL. And if you look at this, the black DLL, the black color one, that means this is a native Windows library, and the red color, that means this is the additional library. Okay, maybe it is installed by another application, by another service, or any other system, or any other Windows system. Okay, all right. The other good news is most of this library, especially the native Windows library, and they always stay in the exact or in the same location memory, and even if you reset the machine. But there is some, of course, there is some exception. All right. Okay. Normally, researcher they will try to use MS VCRT.dll to search for the jump ESP or user.dll or GDI or kernel 32 NTDL or any others. You can pick. You can choose one of the library. So for example, I'm gonna choose this one, cell32.dll, and then this is the shell32.dll, and then in here I'm gonna click on search for command, and search for this jump ESP command. So hopefully in the shell32.dll they have jump ESP. Alright, we found in here the jump ESP in shell32.dll is in this address. This address 7C A58265FFE4. This is the jump ESP. In the opcode is FFE4. Alright, so I'm gonna take this one, copy, edit to clipboard. Alright, so we managed to find jump ESP, okay, in this address. Okay, this is when you are going to do a vulnerability research, you must write down all the information that you collect. So in order later on, if let's say you want to publish this vulnerability, and you want other people to try or replicate into a different system, they know from where you borrow the jump ESP. So you must write in here that we can get the jump ESP in this address, that we borrow from, that we can get from where? What is the DLL just now? Shell32.dll. Okay, and another thing is the operating system Windows XP, XP Service Pack 2, okay, and then the version English version. Okay, why? All right, like I told you just now, most of this DLL they always stay in the exact memory location. Okay, even if you restart the machine and so on, they always stay in the memory location. We haven't talked about protection and any other. This is the basic concept of buffer overflow. Okay, nah, but the location of the DLL maybe will change. Okay, if let's say, okay, in here this is a Windows Shell 32.dll. This DLL will be changed, the location, if there are a few conditions. First, if you upgrade your OS. Okay, from Windows XP to Windows Vista, for example, or Windows 7. Okay, of course, it will replace the DLL. All right, or if let's say you update the service pack. Okay, from SP2 to SP3, it will replace the DLL. Or if let's say you change the version like professional or home edition, or the language, from English version to Chinese version, Japanese version, Arabic, it will replace the DLL. So that's why in here you must put the information that you are going to borrow jam ESP, okay, from this specification, from this OS. Okay, so we know jam ESP is in 7C A58265. So on the next, right now you get the ID, right? Okay, so on the next step, we can put in here, okay, the address of jam ESP, which is in here in 7C, okay, and then A5, okay, all right, and then what next? In the at 5 space 82 and then 65. That's good. Yeah? So now let's try, let's imagine when the buffer is safe and when the buffer is overflow exactly in this point, EIP will be replaced by this address. Okay, so this is the address of jam ESP that we borrow from cell32.dll. Okay, EIP will be replaced to this address, of course, and then after that in our CPU, the IP will be in here. Okay, all right, the IP will be 7C and then A5, and then A5, all right, and then 82 and then 65. Okay, so what will be happen next? Okay, now you get the idea. So our CPU will look at this address. Okay, and then CPU will like, okay, will go to that address, okay, which is pointed by instruction pointer in here. Okay, I will go to 7C F58265 and execute the instruction there. But when our CPU go to 7A65, it will actually go to the cell to the RL, where in here is jam ESP. Okay, so basically, we're gonna trick the CPU, yeah, to jump twice. When our CPU go to this address, actually that one is jump ESP. Okay, so that means after that CPU will look at this. Okay, CPU says, okay, I will jump to ESP. Okay, I will jump to ESP. That is the idea. Wonderful. All right. Okay, that's good. Okay, so now let's prove it. All right, and jump ESP, and then we'll execute. We'll go to GMSC. No matter the value or the stack, the memory position on the stack, then we just go to jump ESP. That's great. Make sense? Okay. Now I will try to create a. We're gonna try to create a proof of concept in here. Right? We're gonna try to put the jump ESP address to that overflow buffer, and then we're gonna check. All right, so I'm gonna have another skeleton, exploit skeleton in here. Nano dot slash minisploit3 All right, okay. Now if you look at this, this is the get, and then 41 41 41 17 87 AAA, the buffer when it's safe buffer. And then after that, when you are going to replace EIP, okay, look at this, a little bit different. You must write in here in the reverse format. This called little endian, because we are dealing with the personal computer. If you are in the mainframe, you can write in the sequential order, but this one you must reverse 7C A5 A2 65. Okay, so this is, yeah, you can put information jump ESP from shelter to DLL in Win XP72 English version and blah blah blah. Okay, and then what is on the next part in here? Okay, we haven't talked about the payload yet. Okay, so in here, and just for the next proof of concept or for next lesson, we're gonna put another part in here. Okay, I'm gonna use green color, for example, in here, the CCCC part. What is CCCC? Remember, be careful. After we managed to trick the CPU to execute the payload, but in this stage we haven't decided what will be put in the payload first. So okay, to make it easy to understand, and to check whether we really calculate the exact location, we really calculate the byte before its overflow. In whenever they go to the stack, I'm gonna put another this string first. C C C C C C C C C C C C C C. Remember, we haven't decided what will be in the payload yet. Okay. All right. So we can compile this one. All of our code. Okay. But before we execute this one, minus.3.py, we need one more thing, guys. We need to set up the breakpoint. Okay. Why? Because we don't have the payload yet. I'm afraid if we calculate precisely, EIP replaced with the jump ESP address that we borrow from cell 32, but then after that our CPU will jump to the stack, which is in the stack we don't have the payload yet. Okay, so otherwise, if they jump to SP, and then they will execute CCC, and then application will crash again. So in this case, you need to set up a breakpoint. Okay, so I'm gonna run in here a debugger again, and then I will restart the application. Okay, so we already start the application, but before we run our third exploit skeleton, I'm gonna view the executable modules. I go to the cell 32 and then search for jump ESP. All right, and in here I'm gonna put a breakpoint. What is the meaning of breakpoint? Breakpoint means before they execute this one, okay, before they before they go to this jump ESP, our application will be paused by the debugger. Okay, so I am gonna run this one. All right, look, this is the breakpoint. Okay, and then we can also run our Wireshark as always, and then restart capturing. Okay, we just in this third example, we just want to check whether we calculate precisely the location of the buffer, and if we calculate precisely, we can manage to replace the IP with the jump ESP address that we borrow from cell 32. Okay, but before that, yeah, exactly before the CPU jump to ESP, it will stop by the debugger. Okay, and this is important part. Okay, because we don't have the payload yet. Okay, all right, everything has been set. Now we can try to execute these modules. And then let's see in here. Yeah, look at this. All right. Get a for 1787 characters, and then and then it's supposed to jump to ESP, but because we set up the breakpoint, it will stop. Yep, that's cool. That's good. Look at this, only debug, min0.txt, and then yes, we can check in here. Our application is paused, and then look at this breakpoint at cell 32 7C A5 A265. Wonderful. And then look at this, our application stop exactly before jump to DSP. Why? If you look at this, right? Okay, I'm gonna move this one. All right, look at this EIP. There's a red color in here. That means this is our breakpoint. This one breakpoint. Okay, and then look at the stack. Okay, wonderful. Our stack is now filled in with the CCCCCC, which is this gonna be our payload. If you scroll up, then you will see. All right, look at this. This is the AAA. This is the AAA. How many bytes? 1787. All right, and then this is a place where we replace EIP, replace the return address, EIP, and because we put the breakpoint, so it will not jump to here. It will stop directly in here. Okay, good, well done. The next step is first what we're gonna do, what we're gonna put in here as the payload. Okay, remember, yeah, when we learn about exploiting, as always, I always say choose the simple payload and the small payload as you can. For example, choose the payload that will just only give you the shell. Choose the payload that will give you the command prompt. Okay, don't use the fancy payload like VNC inject and so on. Why? First, because this is the stack, and this stack is dynamic, and this stack is used by all the application in the operating system. First is we need to find the size, the available size, okay, for the stack, for the payload, okay. So if you look at this, our payload start from this address CCCCC, from this address, and then if you scroll down again, look at this, our CCCC landed in this address, okay. But this is last CCC, but be careful with this because we don't know what is or who or what is the or who belong, or maybe the another application they want to use this application as well. They end this location the part of memory. Okay, to make it simple, yes, to make it simple, to make it not simple, to make it secure. Okay, you must calculate the stack first. Okay, first we need to find the size. All right. So we have now another. Okay, what to put? What to put in the stack? In the stack, or basically as our payload. Okay. Secondly is, secondly is what? You need to calculate. First, calculate the space in the stack. Mm, okay, and then inject uh, inject our payload there. Okay. Okay, first, okay, we need to calculate the space that is available on the stack. All right. Okay, first, to make it easier, try to look at the bottom of the stack, in here. Yeah, this is actually the top of the stack. But in here, if you want to take this one, it is very risky because we don't know what is this. Okay, so my suggestion is try to get one line or two lines. It will be more safer. Okay, I'm gonna select the last address in here, copy to clipboard. Okay, okay, so this is the address of the last stack. Okay, and then after that, where is the address of the first stack? In here, and then copy to clipboard, and this is the address of the first stack. So this is the bottom, the last CCCC in here. Okay, the first CCCC is in here. Okay, and then you can just calculate. For example, from here, this one. Okay, calculate the space. All right. Calculating the space for the payload. Okay, minus this one. Okay, equal to something. Okay, how to calculate this? You can use calculator. Make sure it's a programming scientific or programming mode, and then we can copy this value. Okay, hexadecimal. All right, and then minus this one. Okay, is equal to, oh, sorry, hexadecimal. Oh, no wonder. Oops, Oops, this one. Okay. So this is the hexadecimal base. Oops, sorry. Okay, minus the first CCC equals to 1A4. 1A4, 1A4 in hexadecimal. That means in decimal is 420 bytes. Okay. So this is the maximum size of our payload that we can put. Okay, yes, yes, yes. So now you can understand why last time, if let's say, okay, I'm gonna run MSF console, the old Metasploit, and then if let's say you look at the information info in here, info is 5050 printer overflow, and then you can see in here, look, payload information. Okay, the good exploit developer, when they create this exploit, they will tell you in here that you need to use a payload that no more than 900. But because they already calculate the space of the payload, okay, so now you know the reason why you need to choose the payload or the cell code that is less than 900. But in our case in here, we need to choose the payload that less than 420 bytes. Okay. The last one is, okay, we need to find a cell code. A cell code. Okay, why is called a cell code? Cell code is, why is the name is cell code, is a code to run a shell. Okay, to inject in on the stack, into the stack, into the stack, the stack. Okay, so how to find the cell code? Okay, again, you can. There are many options. First, you can create your own cell code. Eh? Create your own cell code. Create your own cell code. Cell code. Okay. How to create the own cell code? Very simple. For example, create a simple application apps using C or any other, using C++ or any others, to call cm.exe. I forgot the syntax, but it is something like this: exec ve and then cmd.exe. Okay. All right. And then after that, second one is compile. Compile it. Yeah, so it's gonna be, for example, call cmd.exe. And then the third one is disassembler. Assembler it. Yeah, so it's gonna be assembler mode. And then after that, use what? Convert into opcode. Okay, why? All right, because we are dealing directly with the processor. We are going to inject a code in here, to the stack. Of course, you cannot just put something like this: exec, exec cmd.exe, like that. You cannot put something like that because this is, we are going to inject directly into the memory, and this one, it must be in the processor or machine language, or basically this one is called opcode. And opcode is different. Opcode in different depends on operating system. Opcode in Windows, Linux is different, and then architecture, 32-bit, 64-bit, and then the processor. Intel opcode, AMD opcode, ARM, they are all different. Okay. Okay. So what is the best solution? Okay. There is actually to put, or to what you call this, to create the cell code. You can create your own cell code. Yeah. But in this class, don't worry, we are not going to learn about to create your own cell code. We can use the ready-made cell code. Okay. Okay, because if you want to create a cell code, I will show you the book, Cell Coder Handbook. Handbook. And this book, I can tell you, if you go to Amazon, this one is this book is 744 page. Okay, how to write the cell code, how to write the really good cell code. Okay, okay, but don't worry, guys. Okay, we can use the ready-made cell code. If you have time later on, you can write your own cell code. All right. Okay, so a lot of already made shell code. For example, you can go to our exploit DB, and then you can go to here. Look, they have a shell code, exploit database shell code, and then look at this. This is a Linux 32-bit 800 reverse TCP shell dynamic IP port shell code, Linux blah blah blah, Windows 64 shell code, exec VE. This one to execute bin shell. Okay, the smaller shell code that you can get, the more good is your exploit code, because um, like I told just now, we never know how big is the size for the shell code. Okay, we don't make sure, we cannot make sure how. Okay, look, if you look at this shell code in Linux x50, x48, x17, and so on, so on. Okay, one of my favorite to get the shell code is by going to shellcoder database. Okay, if you look at this, and also I want to show you in here, for study case, that every shell code is different, depends on the machine. Look at this, this is shell code for the AIX, just to execute bin shell, 88 bytes. Okay, if I open this one, look at this is after the disassembler, and this one is just the shell code itself. But this is for the AIX IBM. BSD, Cisco, SCO, FreeBSD, 64-bit, 32-bit, 32-bit, HPUX, IRX, Linux. Everything they have different shell code. So that's why shell code is very specific to each of the operating system, processor, architecture, and a lot of, for example, distribution, if Linux, and so on. Okay, I will just go to the Windows shell code. Look at this Windows 64 shell code, obfuscated shell code, 32-bit 64. But this shell code, look at the purpose. This shell code will just download and execute, use PowerShell generator. This shell code is just to add admin, ADML, IPD, and so on. Okay, remember in the Metasploit in here, you can use payload. Show payload. All right. Okay, then you will see a lot of payload, and if we look at one of the payload, for example, info win32, win32, okay, underscore bind, one of our favorite payload. This payload is Windows bind shell, the size is 317, and then listening port, and then look at this payload will just listen for connection and then spawn a shell. Okay, all right, so for example in here, you can choose. This is one of a good payload. If you look at this payload will give you a command prompt execution with XC, and the size is very small, 23 bytes. But if you want to use this payload tested under Windows XP, SP2 English and Arabic version. And this is the assembler, and this one after that they compile into the opcode. So we'll see X8B, XEC, X66, and so on, so on, so on. Okay. If you want to check in here, okay, I will go to the hex to assembler language. Okay, online hex assembler. I will try to get one line in here just now from the shell code. Okay, this assembler that one. Okay, remove here, and then disassemble. Then you can see in here this the move EBP budgets and so on, so on. So this is the string in the hex code, because we are going to inject directly in here into the memory. Yeah, so to make sure that your shell code fit in, and make sure that your shell code is compatible with the target machine. Okay. Okay, the other things which is interesting is, if you want to try, you can download the shell code from the shellcoder database like just now, and then maybe you need to modify, same, because this is the what you call this. This is the raw shell code. Look at this, and the shell code we just add new local administrator and test it on Windows XP Pro 32-bit, blah blah blah, and so on, so on. Wow, very difficult. I mean, not difficult, quite complicated. How they can create this? Okay, now I'm gonna show you the easy way. Yeah, this is just to at least you understand. Then later on you can explore how to write your own shell code. Okay, remember in the Metasploit you can extract. They have a lot of payload. Okay, so in here I'm gonna use Metasploit again. Yeah, thanks to the Metasploit, because we can extract the payload. For example, in here I'm gonna use Metasploit if this Metasploit version 3. you can use MSF payload. So if I look at this MSF payload, Windows slash shell slash bind TCP, and then view in the C language like that. Okay, it will show you. It will Metasploit. Remember, you can extract the payload. Remember when we talk about backdooring, you can extract the payload into one application. Okay, so remember when we exploit, you can set up the rocket, and then after that you can set up the payload. Payload is the head of the rocket. And if you look at this, yes, 298 byte stage 1. Okay, what is the meaning of stage? Because Metasploit have a function if you want to, for example, to extract the payload as well. Okay, and then you can see from here, and this is the payload, to just to simply 240 bytes, and all of this just a payload to what they call this, to give you a command prompt. Okay, in this case, I will just go to the advanced payload. I want to create a payload that connect back to our machine. So, for example, we are going to exploit this machine, and then when the exploit attacking or manage to attack the service, okay, and then I want my payload to connect back to our machine. Okay, what is the payload names, or what is the category of the payload? That one is called reverse payload. Remember that? So I want the payload after they execute or explode on the remote machine. I want the payload to connect back to our machine in port number 443. What is this payload name? Reverse payload. Okay, so this is, yeah, just to give you a challenge later on. Okay, I'm gonna create a reverse payload. All right. Okay, clear. Mhm. So I'm going to put the reverse payload in here. For example, MSF payload. Please create for me Windows slash shell slash reverse bind TCP. Okay, and then don't forget, reverse Windows shell. Okay, Windows slash shell reverse underscore TCP, and don't forget to put the listening host. For example, this is the researcher machine, and then L port is port number 43. Okay, port number 43, and after that, I want to show it into the C language. Oops, sorry. MSF payload. Okay. Windows shell reverse TCP L host L port 443. Okay, because I want the payload to connect back to our machine. Very cool, isn't it? Alright, so just wait until our Metasploit will generate the payload, and then after that just wait for a moment, then you will get the raw payload in the opcode. Okay, the payload in the opcode. Look at this. This payload is only 240 bytes, but if you look at this later, you will see there's something which is interesting in here, x00, x00, and so on, because actually you cannot use x00. This is called bad characters. Okay, what is bad characters? X00, if you inject this X00 into your payload, X00 mean null character. So if your CPU try to execute this one, next is this instruction, next is instruction, and when the CPU they go to this X00, this is null. That means your CPU will just stop, so your payload will not working as well. Okay, so that's why in Metasploit we can also use MSF encode. Okay, later you need to find out why is this. Find it in later by yourself. MSF encode architecture at 86, x86. Okay, and then please bear this character. For example, okay, I'm gonna remove the slash x00 slash x00, enter like that. Okay, I'm gonna put in the row, and then oops, sorry, row message, blah blah blah, code. All right, and show it in the screen. Okay, row. Okay, enter. Now later on it will try to remove the x00. Okay, anyway, after the what we can encode, like I told you, in MSF payload you can encode the payload to use Shikataganai to the evade from antivirus, You can encode interpreter, you can encrypt the payload, and so on. So many options in the Metasploit is very good, right? Okay. So, but in this case, I'm going to use a simple payload to connect back to our machine, and let me try to look to show you the last of our exploit skeleton, or basically our exploit code .py. Enter. Okay, now we'll see something, some new things in here. Okay, the first few line is the same. Import user bin Python import socket target address target port and then buffer get space. And in here, just now I use A, 41 41 41, but in the real exploit you can use X90. X90 is NOP operation. NOP operation in assembler, that means if our CPU they go and they meet this XNOP instruction, they will not do anything. Nope, they will just go to the next memory location address without executing something. Just go travel to another memory address. In case I put or I miscalculate the size, so our CPU will not go or inject it, or if let's say if this place is injected by another code, so our CPU will not jump to another location. And then after that, this is the jump ESP from cell 32 in XP2's English version, and this one is the payload cell reverse TCP connect back to our researcher machine in port number 3 row, and this one encode and then remove the bad characters, and this one I add another encryption shikataganai, yeah, to evade from antivirus. And then you will see in here we have what we call this as nopslet. Okay, what is nopslet? Nopslet is some of the additional characters. Normally if you put the payload, if let's say I will go back to the machine in here, okay, in the machine, in here, sometimes if you just directly execute the payload in here, sometimes it doesn't work because it depends on the processor itself. Sometimes if you just jump to the ESP, if your computer in some condition there is an antivirus or something like that, it will directly skip some of the lines of your payloads. Okay, so maybe it will jump to this here. So you need what we call this as nopslet, a few bytes of the space, so your CPU will have time to go to the or will take a rest or take a break for a while before executing our payload. That's one of the theory. The other theory is because you encode your payload using encryption. So whenever the payload will be executed in here, the payload need a space to extract. It's same like when you compress a file, and then when you need extra space to decompress or unzip the file. So how to find out whether this is 16, 20, 30, it's up to you. There's no exact calculation, but normally people use 16 byte, 20 byte, 30 byte just to make sure that our payload will be running well. Okay, so I have already the last exploit code, and then now we can try to execute that one /minisploit4.py. But be careful before we execute this one first, because this payload will connect back to our machine. So I need to set up what? Set up a listener. Remember what is listener? When we talk about backdooring, listener is to listen, to open the port in, to open a port in the machine to accept a connection. You can use netcat, you can use exploit multi-handler, but in this example, I'm going to use netcat, the simple one, listen in port number 43. Okay, enter. So we are ready in here. If our calculation is good and is correct, and if our payload is good as well, when we execute this exploit, it will connect back to our machine, and here we will see the command prompt from the machine. So I'm going to restart in here, restart the application, restart, click on yes. Okay, tada. Okay, do you need the breakpoint? No need, because we already set up the payload. Now we can just start the application. Okay, I'm gonna click on play. All right, click in here, click OK again. All right, and then if you want, you can run Wireshark to see the traffic, capture, restart again. All right, then you will see in here we are already in Wireshark, and then now we are ready to send our exploit. And okay, let's just cross our finger. Look at this, get to 2020, which is our knock operation, and then after that EIP will be replaced by what, by the jump ESP that we borrow from cell 32. And when they jump to ESP, our payload is already in the stack. And look at this, wonderful, look at this, we can see I got the connection from the remote machine. Okay, and we are already on the remote machine. So wonderful. If we look at this, you're already on the remote machine. You can do whatever you want. Net users, for example. Okay, we already who am I? Do I have who am I? Or didn't have it. All right. Okay, what happened in the application? Is the application crash? No, and because why? The application is not crash anymore because actually we redirect the flow of the application to execute our payload. You can, however, later on explore and play around with this. Look at this information. All right, it is still running. And if I go to here, I want to follow this one. Follow in the register if you want. Okay, origin. But yeah, later you can just explore what is value, the value on the stack. I will go to follow in DAM the stack. Okay, this is the value on the stack, which is, oh, just now I don't put a breakpoint. This stack is actually connect back to our machine. So you can also try to check in here command prompt netstat this an, and then netstat this an, and then you can see, yes, we managed to create our payload connect to port number 43, and we can get the command prompt, and then without what exploiting or without crashing the machine or the application is still running. Okay.